Okay, so we continue. The next talk is about a project that's now called Airprobe, that had a number of different names before, one among them GSM Scanner. The goal of Airprobe is to provide a set of tools that enables you with an USRP or GNU Radio hardware component to sniff GSM off the air, decode the protocol, make measurements, and basically be a general purpose development tool for everything GSM over the air.
Okay, hello. Is this working? Yeah. Okay. I'll probably wait for a couple of more seconds until people have settled on their seats. For those of you who have been attending the last talk, I now have some statistics here on the screen. Just going to finish that before going on with the actual other topic. So this is the number of, connect request. Well, no, rather start with the green one. Setup indication. This is the number of calls that people have tried to make over the time. So you can see up to here, basically we were still doing build-up testing and so on. And on the 13th of August at around 2 p.m. we started to make the network public, and people were actually using it and starting to make calls. So this is the number of calls that people were trying to make. The red line is the number of calls where the recipient was actually available. So the recipient, could have switched off his phone or could have been, switched back to his commercial GSM network and so on. And then the blue line is how many people actually picked up their phone. So you see there's, many people have decided to leave the network and are not reachable anymore. And then even out of those people, a high percentage is not actually picking up the phone. This is the kind of statistics you can draw, and we continue this and see. But also what you can see is, well, at least until about 24 hours ago, the number of subscribers was already above 400, but not even every single subscriber ever made a voice call. So please use the network more, make more phone calls, send more SMS. We really want to have more load on this network. Okay, we also have what was missing from the last talk, and I'm sorry for the delay. Where are we? Here. We also have this, relationship diagram, who sends SMS to whom. The numbers here, this is anonymized, so these are not the phone numbers in this diagram. This is just anonymized, so you can see, but you can very clearly see that there are always like networks. So like these 4 people apparently know each other, so they've sent a couple of messages back and forth. Well, actually quite a few, 13, 20, something like that. And then there is this big blob here. Well, 3 is me, I can say that. Obviously, did a lot of testing with a lot of kinds of people and sending test messages back and forth. And you can see, well, it extends to down here. But then typically it's like 2, 1, well 6 is already quite high number of messages. And then here you have all of these islands. So again, a couple of people who know each other, a couple of people again, maybe only 2. Those 2 have actually sent 24 messages, quite chatty. 41 here. No, it's 4 this way. Sorry, yeah. So this is 2 and 1 message, 2 and 4 message. It's not that many actually. But here, what is this, 23, 2, and 1. So 23 is definitely a high number. But it continues all the way, and you see all kinds of islands. So apparently not many people know each other or communicate with each other. It's all only within a small group, but not, with many other people. Yeah, well, so use more SMS messages. And I mean, it's free. It's free. You can send more messages. So maybe you might want to send random messages to random people and say, who are you? It's free. Okay. Now, different topic. Yeah, well, you know, yeah, whatever you want to say. Yeah, Airprobe. So this presentation is about a project called Airprobe, and it's about monitoring GSM traffic with hardware just like the universal software radio peripheral. I'm going to talk all through this in a couple of minutes. So again, the question why? You know, why would you want to monitor GSM traffic? Well, because you can, obviously. Because the protocol is not, you know, designed in a way that entirely prevents you from doing that. Also, for the same reason that you might monitor other networks, to learn and experiment with technology, and well, also to do things that people haven't been doing all that much so far. You know, war driving with Wi-Fi cards, you know, it's old. You know, finding whatever open Wi-Fi networks, breaking WAP keys, you know, must be getting boring for these kids at some point. So that, you know, there's other networks that are publicly deployed and that have massive security problems. You know, DECT is one of them, and you have seen at last year's CCC Congress what has happened to DECT security after a couple of people have looked at it in more detail, probably the first couple of people in whatever, 10, 15 years. And for GSM networks, it's also the same. These networks are deployed, and you know, the industry is very closed. They don't really get much input from the general IT security community, and they especially apparently don't like to improve their security. So by monitoring GSM traffic, you can be basically, again, one step closer to demonstrating, to actually practically demonstrating the known GSM security problems. And that, again, can help you to raise public awareness, just like operating your own network is one of the tools, one of the foundations that you need or that can help you to raise the awareness about GSM insecurity. Again, legal disclaimer, you know, don't try this with public networks. GSM operates on licensed frequencies. You're not supposed to be accessing those frequencies. Most countries have telecommunications privacy laws, which you're breaking if you do this on production networks. That's why we're building a test network here, so you can do all that legally. You can obviously monitor, capture, analyze your own network, right? And you have to if you operate your network. So the software, again, is only for research purpose. What is airprobe.org? It's a platform for GSM protocol decoding software, including website, wiki, mailing list, Git repository, and so on. It's formed by a bunch of people who first met at the THC GSM mailing list. And the project is now hosted by the Chaos Computer Club. What's the goal? Well, the goal basically is to produce a open source GSM protocol decoder using a software-defined radio, doing the layer 1 demodulation, protocol decoding. Oh, I'm getting, you know, fog. It's dramatic. Special effects. Has somebody hacked that machine? Can you do this again? Yeah, so you do the layer 1 demultiplex, demodulation, decode, the TDMA demultiplex, recombining the bursts into MAC blocks, and so on. All the low-level parts of the RF protocol, and then handing off the layer 2 MAC blocks into a protocol analyzer like Wireshark, or you know, other protocol analyzers that you might write or you might have. You know, the reason why people are doing so much security analysis and playing around with TCP, IP, and Ethernet is that simply because, you know, you can buy any random PC, even a whatever old PC. Most likely these days it has an Ethernet board on the main board itself, or you can put an Ethernet board inside, an Ethernet card inside your PC. And then that's basically everything you need to do Ethernet, TCP, IP-based security analysis, protocol analysis. Everything else is software. You have an open source operating system where you can influence every aspect, how it talks to the Ethernet card. You have open source network protocol stack implementations where you can actually intentionally, intentionally, whatever. Yeah, maybe somebody can close the door over there, please. Not sure. Well, fresh air is actually not too bad an idea either, so I'll just continue to talk. If it's too noisy, please complain. So we're all going to die in here. Okay, leave it open, leave it open, leave it open. You know. Did somebody say Jehovah in here? Oh, sorry. So, what? Sorry? No, nothing here. It's not my phone. So, anyway, handing it off into a product analyzer. So what's the reason that people cannot easily do this? Well, as I said, in the Ethernet world, you plug in an Ethernet board, you set it to promiscuous mode, you receive all the frames, you decode them in open source software, or you actually generate or receive them from open source software, and then you can change the aspects of the protocol. You can send flags that are not meant to be set together. You know, you remember the XMS bits in the TCP header. You know, old stuff in the TCP/IP world, but nobody has been doing it in GSM, at least not to anyone's public knowledge. So the GSM networks and other networks are just lacking all that, you know, that I would call it reliability testing. You know, that other networks have experienced over the last decades. And the reason for this, you know, even with Wi-Fi, you can buy a Wi-Fi card, and, you know, many of the cards, or most of the cards today, you can switch in promiscuous mode, you can receive all the frames that you're getting. You know, you have the entire protocol and software if you want, at least with a softmac, a Wi-Fi card. And you can, you know, you can start to play with that technology. But with GSM, the problem is that there is no real, you know, free market of the equipment vendors, of the component vendors. If I want to build a mobile phone, or if I want to buy a digital baseband chip for GSM to do anything, to build whatever, to build a protocol analyzer, to build a phone, to build a base transceiver station, the kind of chips that the market offers, the chips the semiconductor industry offers, they don't sell them to you. You know, you can tell them, oh, I want to buy this chip. No, thanks, go away. If you do not, you know, come to them and say, well, I will buy 10 millions per year, they will not be interested in you. And no matter what protocol analyzer you will design, you will never sell 10 million units per year of them, no matter how good it is. So you don't have access to the components that would give you the low-level access to the bit stream or the layer 2 of the GSM protocols. Every mobile phone has those protocols implemented, and they're implemented in proprietary software, and the proprietary software is typically, you know, locked down, cryptographically signed, maybe encrypted, and it runs on hardware for which no single bit of public documentation exists. So even if you manage to, you know, break the signature mechanism of your GSM baseband, like it was done for the iPhone unlocking and for many other projects that hack on mobile phones, you also still have to reverse engine. Well, obviously you can disassemble the binary code and so on, which obviously you're not allowed to do, but you can. And maybe you can change something in there, but you have no understanding of how the hardware works, because those vendors don't give their documentation to anyone. Even cell phone manufacturers rarely get the full documentations to the components they're using. You know, all they get is, well, you know, this is the electrical characteristics, this is how you connect it on your board, and then here is our software, and, you know, that's it. They rarely get to understand the details of the actual, you know, DSP and its peripherals, and how everything is interconnected, and how the time processing works, and so on. So this is a big problem if you want to do GSM security analysis. Again, you can read all those specifications, and you can read all the scientific papers, and then you can go to another scientific conference and say, well, based on what I read, there must be a problem, you know. And then you get applause for that, and then you go home. But nobody, that it doesn't really have any impact, right? The impact will only start to exist if you can practically prove there is a problem, and you can demonstrate the problem. In order to demonstrate the problem practically, you need access to technology that gives you access to the bit stream, to the lower layers of the protocol. The nature of the industry surrounding GSM technology does not give you access to that technology, so you have to find a way around that. And one of the ways around that is basically software-defined radio. And this is not only true for GSM, it is very much true for all the other communication protocols out there for which you cannot get low-level access. Even in your DSL modem, for example, you do not get access to the layer 1 and layer 2 that is spoken on the DSL line. This is all in some chip that does whatever magic, and you get some ATM, maybe ATM, but most likely only Ethernet frames out of that, and the lower layers are hidden from you. If you want to have lower level access, you do not get documentation, you do not get access to the code or anything that implements these protocols. And the same is true for DEC, the same is true for many RFID systems and so on. So the universal solution to all these problems is software-defined radio, which is a modern technique where analog hardware is replaced by software, and digital signal processing replaces analog electronics. There are different variants for how you can do software-defined radio. One of them is directly capturing the carrier frequency using an extremely high-speed analog-digital converter, which is very expensive, and you can only use it for relatively low carrier frequencies. So it's not a practical option yet. In a couple of years, it's probably much more practical. What's more practical is you down-convert the RF signal. So let's say you have a 900 megahertz GSM signal. You use an analog down converter, you multiply, you do an analog down converter to transform that to, let's say, 10 megahertz. And then the 10 megahertz you feed into an analog digital converter. And from there, you take it and you do mathematics, digital signal processing math, to decode and to synchronize and so on the bits that you see in air. There's a different, some people also claim it's SDR, but I personally don't believe that. If you actually do the demodulation in hardware and then feed the baseband signal into an analog-digital converter, some people say, oh, this is software-defined radio. I think it's just a marketing trick. It's a traditional analog receiver. But anyway, by moving the problem out of hardware for which you don't get documentation into the domain of software where you can do whatever you want as you as a programmer are used to, you're the god of the software that runs on your system, you can basically, we can start to attack these problems. And one approach to to attacking the problem is GNU Radio, which is a GPL license-free and open-source software project for software-defined radio. You run it on a general-purpose PC. You don't need any special-purpose DSP or whatever kind of board. You have building blocks like filters, demodulators, FFT, and so on as building blocks, and you script them together using Python as a glue. You run it on Linux, on macOS, on BSD, on Windows, and it supports different hardware. And the only hardware you still need is this USRP, which I have conveniently in this small box here. You can buy that for, I think, about 1.3K euros. So it's somewhere between 1,000 and 1,500 euros, the complete setup, including the front-end boards. So it is the ideal companion for a software like GNU Radio. You have a modular main board which has analog and digital converters and so on. You have pluggable front ends. So when today you want to listen to GSM, you plug in the front end for GSM frequency range, such as 900 megahertz, such as 1800 megahertz. If tomorrow you want to tune into a different protocol that runs on a different frequency, you plug in a different board and you receive and decode it. Sorry. A USRP mainboard has a couple of front ends. For GSM, you can use 3 front ends. There's the RFX 900 for GSM 850 and 900 megahertz. There's the RFX 1800, which you can use for 1800 and 1900 megahertz GSM signals. And then there's the DBS-RX front end, which is a receive-only front end, sufficient for protocol demultiplex, which you can use on all of the frequencies. However, the sensitivity is very low, so you can only receive strong signals with that board. So what kind of software do we have in Airprobe? We have 2 programs called GSMSP and GSSM, which were the 2 earliest implementation. At least GSSM is by Joshua Locke. It's considered early alpha level software, has many receive errors, even with relatively good signal. So by now, I think almost nobody is using that software anymore, but it was milestones in achieving a freely available open source GSM receiver. What came next was GSM T-Void, which is, for a long time, it has been the best decoder for GSM that has been available. It has a relatively comfortable UI where you see the frequency spectrum and you can, you have a slider for the channel and a slider for whatever. It actually has a user interface that many people consider a user interface. Now the latest component, latest addition of receiver software for doing the actual decoding and getting the bits off the air is GSM Receiver, which was written by Piotr, and it has a much better decoding accuracy than any of the other ones. So by now, if you want to play with this, I strongly suggest, make your own opinion, but I personally and other people believe the GSM Receiver is the best approach right now. It is still far from being complete. So even when you're close to have a good signal reception, you will still see dropouts and you will not get 100% good reception. If you understand digital signal processing, there's a desperate need for people to help with this project. Go to the website, go to the wiki, join the mailing list, help us out. We can use any hand that is there. There is another program called GSM Decode, which is layer 2 plus decoder. So it takes the output of T-Void or GSM receiver and puts it into a human-readable format that you can actually understand the protocol. At the very same level, you can also just interface Wireshark, which has also quite complete support for GSM protocols by now. Still a couple of bits missing here and there, but it's okay. GSM Stack is a Mac layer that I started some time ago, but I didn't really finish it. The idea is just to have a more modular architecture, and I'm working on integrating it with GSM Receiver at some point. So before I go to the actual practical demonstration, I'll leave just that thanks slide, and I'll switch to a different laptop. I don't think the cable is long enough. I'll find a solution. It's not that you need any special laptop. It's just that I happen to have used the software last on this particular device, so everything is compiled and ooh. There we go. Okay, now. Oh, what happened now? Sorry for that. Oh, no, it is actually working. Okay. It's just very, very, very strange. Oh, this is, my goodness. I have a different terminal window here than there. Sorry. This is much better. Okay, now finally. Okay, so basically, just to explain the general setup, you have this USRP device here. It has GSM 900 antennas. GSM 900 antennas that can be tuned, for example, to our test network here. The USRP contains the main board and the receiver front end. It doesn't understand anything about GSM. It's basically just, turning the RF interface into bits that go over the USB cable into this laptop. And then on the laptop, I start software components that are from the Airprobe project or are hosted at the Airprobe project. It's more of a platform for all kinds of developers who work with GSM-related protocol analysis. And also, all the GNU Radio software and the USRP input plugins for GNU Radio and all that software is utilized. So the dependency of all the bits and pieces of software you need right now is still relatively complex, and building all of that, it's a bit uncomfortable. Also, the actual user experience of the various programs is not very welcoming. So there's a lot of work still needed in that area. Okay, now what I have here is a checked out tree of the Git tree of the Airprobe project. You see the individual software components that are in there. What I'm going to use now is the GSM receiver code. In the GSM receiver code, I can start the process to actually turn the bits into something that's useful. So GSM receive has a number of different programs. One of them is GSM receive, obviously, is the name of the program. If you don't call it with any options, it will give you some kind of error. If you call it with help, it gives you some useful output. So what I'm going to use now, rather than using a live capture from the USRP, I'm using a pre-recorded file that I took before. So what you can do is you can record all the data that comes over the air. You can save that in a file, and then you can run the GSM receive on that file, which is what I'm doing right now once I manage to type this line correctly. So basically what it does is it prints you out the hex. Oh, I should increase the font size. So it prints you out the hex sequences for each MAC block. The GSM protocol architecture on the air interface has an architecture where where each principal unit, data unit that is communicated over the air interface is a 23-byte, what's called MAC block. You have 23 bytes. Don't ask me why 23. Everything has odd numbers in GSM. It's 51, 26, 23, never any power of 2. So the 23-byte MAC block you can see here, you see an awful lot of 2B messages, or 2B hex bytes. 2B is the padding pattern that every GSM frame contains. So if a packet is actually shorter than the 23 bytes, it will get padded with 2B. So you see this packet is actually only, 6 bytes long, and the remaining line is just the padding bytes to the end of the packet. So you take the actual analog digital samples, you call the GSM receiver, and it puts you out the MAC blocks that you receive off the air of the GSM interface. Now, obviously, the hex bytes are not particularly pleasing to the human receiver. So there is software that you can use for decoding it, and that's called GSM decode. And all I do is pipe these hex bytes into GSM decode, and once I do that, and I pipe it through less, so we actually see something, you get a decode of the message. So on the top you see the actual message, again the 23 bytes, and then you get a decode of the individual bytes starting here. So what we see here is a radio resource management message, a system information type 4, which is one of these beacons that are regularly broadcasted on GSM. We see, well, the mobile country code is 1 and the network code is 1. Which is, again, a test network. Obviously, I did not take this capture from, GSM networks. Switching it off now. So I did not capture this on a real-world network, but I could capture this very well from any commercial network, because the packets I'm seeing here are not encrypted, not on any network. So what I'm seeing is, the certain configuration about the cell. I see all kinds of configuration parameters that are relevant to the cell. Now let's go to some other packet. So what we see here, for example, is a paging request. It's a request of the network calling a mobile phone to become active. Right? Typically, if you just have your phone logged into the network, but you're not using any calls, then the phone will not make any actual conversation with the network unless the network wants to deliver a call or you want to make a call. And in that procedure, you page the phone. And what you see is, well, there is basically no identity, so it is an empty paging request. So there is no paging right now. It's just a filling packet. You see some more paging requests with no identity. They're all just filling pattern. Then you see things like other system information type frames, system information type 1, system information type, some other system information types, which are all these beacons that are regularly broadcasted. This one is system information 2. The system information frames contain information how the network is laid out, what kind of neighbor cells you have, what kind of frequency hopping is used, if any. This cell here is not using frequency hopping, but that is, so it's simpler to actually receive the data if you don't have frequency hopping. If you have frequency hopping, then the configuration of the frequency hopping is also contained in the actual unencrypted broadcast beacon packets. So the hopping pattern is public knowledge. It's not that the frequency hopping provides any extra level of security. The frequency hopping is just there to minimize interference. So let's say some interference is on one channel and you constantly change your frequency, hop to different channels, and you get less interference. But the frequency hopping, many people believe it's a security feature. It is not, because the hopping pattern is public. It's publicly broadcasted. So, sorry? Whatever. We'll take questions. Either you go to a microphone or I'll take questions at the end of the presentation. I cannot understand individual questions. This is all broadcasted in that channel. So you can decode all that, and you can see description of the channel layout, how the channels are organized. So based on information that is contained in this broadcast channel, you get an overview of how everything is structured, where the channels are, how they're organized, and so on. And you also see whenever the network activates a particular phone. When you activate the phone using a paging request, you will see the temporary mobile subscriber identifier, which is a number that's temporarily allocated. So you don't immediately can make a connection between the person or the subscriber and the messages you're seeing here. However, for example, in the network that we're using here, and the HAR network, to make it easier for people who want to play with this, in the phone book we actually print the temporary mobile subscriber identifier of every subscriber. So even if you don't, like in a regular network, you would not know at this level who exactly is being called right now. But in our network, because we provide that information, it's easier so the entrance barrier is lower to actually play with this technology and to receive the GSM frames. You will see not actually all too much data in here because it's an idle, empty cell. It doesn't really have a lot of activity. So most of the paging frames are empty, and you see no identity here. You can also the GSM receiver also creates a file called gsmreceiver.pcap and gsmreceiverburst.pcap, which are two PCAP files in two different formats. I assume you know a PCAP file is a packet capture that you can use with tools like Wireshark. So instead of using this clumsy ASCII console interface, you can open the PCAP file in Wireshark, and that's what I'm going to do right now. I have to state I'm not entirely sure whether it will work right now. It's so busy with operating the network and preparing the network here. Why did it not? What's the problem? Oh, there is some error. Something is messed up. Anyway, I can open a different. No, Okay, so there are some patches against Wireshark which are in the repository, in the Airprobe Git repository. Here is the Wireshark WTAP GSM.patch. I probably have not applied that to my current build of Wireshark, but using the patch, you can then have a more verbose decoding of the protocol. So this is all still unencrypted over the air. Starting from the paging request and the paging response in a regular GSM network, the encryption starts to be implemented at that point. So all you can see is basically, okay, a phone is activated, and there is a number that you cannot immediately associate with a subscriber, and then you see an encrypted connection. However, that encryption has serious weaknesses which have been documented many years ago and about which the next presentation will be. So if you put all these parts together, right, you have, for example, the possibility to run your own network, so you don't get any legal trouble because you're eavesdropping on somebody else and on a commercial network. You have the actual receiver infrastructure here where we can decode frames off the air, can put them into their hex bytes and can decode them in protocol analysis tools. So as soon as the encryption, which there's cryptographic papers that it has been broken, so as soon as there is a working practical implementation that's readily available, anyone with very little equipment and a regular Unix-like system, a little bit of source code here and there, and this USRP hardware or any other software-defined radio can receive and decode the actual GSM data that is transmitted over the air. So I could try now to actually capture the network that we're running here. I fear it's probably going to take me a little bit too long. Also, the signal reception is very low in this hall. So I think it's more efficient to just take questions and to address your questions, or if you have any kind of make a phone call. But I can make. Well, the signal reception here is relatively low, and the quality of the software decoder also is relatively low. So if I Sorry, my handset has a big signal? Well, I can tell you I have a relatively low reception in here, but I can, nonetheless, if you insist, I can give it a try. But the location in here is not very good to capture the actual signal. The mobile to cell direction has not been implemented so far. It's only the downlink coming from the BTS. The uplink has not been implemented in GSM receivers so far.
May I ask a question?
Of course.
If one were to implement this to get as much call data as possible in a typical urban environment, how many of these USRPs and what kind of calculating power would be needed just to capture, not doing decryption or get the wave file, but basically just to get the encrypted frame?
Okay, so the question, I'm just repeating this for the audience. The question was, in a typical urban environment, how many of these setups would you need to get coverage of all the voice calls? Now, GSM has really many different channels. In an urban environment, the channels are typically very densely used and densely packed. So you can easily estimate a couple of hundred of GSM frequencies are in use in parallel. And the software that we currently have can decode one of these frequencies. Now, the hardware has the capability to capture a number of more channels in parallel. So you can capture, let's say, using a realistic decimator, you can probably capture, it's 200 kilohertz spacing, it's 4 channels per megahertz. So I would say something up to the level of 32 channels is definitely something you can still capture with a single board and just write it to disk. And if you extrapolate that, you probably need at least 10 of these boxes installed at a single location to get a relatively to get a reasonable proportion of all the phone calls that are being made in that very location. So it's still something that's doable. It's not like you need, thousands or hundreds. It's in the tens of number of units you need just to save and store all that data. The storage capacity also is not that much of a problem anymore these days. As you know, the hard disk capacities are increasing so fast. You can easily get a couple of terabytes of storage and put it here on this desk or underneath the desk. And so actually doing offline analysis becomes a very viable option. So if you know that somebody's going to make a call in this area at a given point in time, you can go there, you can deploy your 10 boxes, you can capture all the data for an hour or two or whatever amount of hours, and then you can take all that home and have a couple of machines offline do the actual decoding and further process on eavesdropping on that. So generally, as I said, the tools are here now. They're very, very primitive still. As I said, the user interface is very clumsy. So if I want to actually decode the signal, the first thing I have to do is go into spectrum analysis and see where the carrier frequency is located, because it might be shifted a little bit from the clock. There's many manual steps involved in this. And after the manual steps have been performed, you can make it work, and you can actually get a reasonable output. But basically the proof of concept is here. The tools are available. It's now up to the community to optimize the tools, to automatize the manual processes, and then combine the result of that work with the work of the crypto analysts who are on their way of having a very practical solution to breaking the A5 crypto. And once those pieces come together, I would say in maybe a year, maybe 2 years from now, you will have a Kismet-like setup for a relatively few amount of money. Yes.
Could you tell us which modulation schemes at the moment are possible to decode? Because basic GSM modulation schemes apparently work, but for example, Edge uses higher level modulation schemes which are not so trivial to decode. And I don't know, for example, could you also tell us if GPRS decoding in the aggregate states is also possible?
Okay, so right now the software is all centered around GMSK, the Gaussian minimum shift keying, which is the modulation scheme employed by traditional GSM for SMS, voice calls, and so on, data calls even. GPRS and Edge, GPRS still uses the same modulation, but has different encryption and different other aspects. Edge definitely uses a different modulation scheme. It's I think it's QPSK or APSK, something like that. GNU Radio has modules for all these standard modulation systems. So there is a decoder for QAM and QPSK and all the various standard digital modulation formats. It has not been implemented in the GSM decode yet, but the basic building blocks are there. You need to work on the synchronization and on the actual error correction bits and so on. But that is a next step. I think right now diversifying to different modulation schemes would be probably the wrong approach. First, get the GSM, not just a proof of concept and something you can demo, but actually a working implementation that removes the manual fiddling and optimizing and setting and whatnot. Get that into a very practical shape, and then you can go on for a GPRS. What has to be noted, though, is that the cipher used on GPRS is a different cipher than the one that's used for a GSM, right? So all the work that's currently being done is for GSM voice calls and SMS and traditional data calls, but it is not directly. You cannot directly abstract from that onto GPRS.
Okay, thank you very much.
Yes, hi, great stuff, thank you. I have a question. I'd like to know, would it be possible to use the device you acquired on eBay in combination with OpenBSC to sniff packets and interpret them at the same time?
No, that is not possible. The GSM is a very asymmetric architecture. The receive and transmit frequencies are completely different. So in your handset, the transmit frequency is 45 to 80 megahertz different from the receive frequency. So a handset has receive and transmitters at the opposing frequencies than the BTS. So that's one of the reasons why even if if you crack all the software on the handset, you could never make the handset appear as a BTS in the network. It's a physical limitation. And also, if you want to do sniffing of the downlink, what's coming from the BTS, you need to be a handset-side receiver. And if you want to sniff from what's coming from the handset, you need to be a BTS-side receiver. So if you use any of the two end equipments, like BTS or mobile station, you can never receive both directions with that equipment.
Hi, you mentioned frequency hopping earlier. Do you currently have support for following that? And if not, what's missing that you're going to need?
I unfortunately did completely not understand your question.
Do you currently support frequency hopping?
Do we support frequency hopping? Was that the question?
Yes.
Yeah, the current receiver implementations do not implement frequency hopping yet. There's different approaches how to solve the problem. One approach is to actually implement the frequency hopping in the USRP and then just download the pattern that you have decoded from the beacon channel into the USRP, and it does the hopping. There is another approach where you just typically, at least in not too big cells, let's say you have 4 or 8 frequencies that are being hopped. So since the receiver front end is relatively wideband, you can capture all of them at the same time and then implement the hopping in software. Because if you capture wide enough that all the frequencies that it is hopping are inside your capture, then you can use filtering to select the individual parts in there. But to my knowledge, at least in the Airprobe and THC GSM project, nobody has implemented either of those two approaches yet. Yeah, it's a question over there. So the question was whether the hardware supports multiple frequencies for TX and RX. And yes, the USRP hardware, the USRP version 1, has 2 different versions of the hardware, but both are available. It's not like one is phased out. The version 1 of the USRP board has 2 receive and 2 transmit sockets for front ends. So you can put 2 modules for receiving on the board, and you have 2 analog digital converters, so you can simultaneously receive on the uplink and on the downlink channel to actually decode both at the same time. So the hardware has the capability. Software, once again, is not there yet. We're still at the downlink. Uplink is next step. Frequency hopping will follow afterwards. So once again, if you are familiar with communication systems, if you have any idea about signal processing, and you're interested in helping this project, there is still a lot to be done, and we're very happy for any contribution in Airprobe. Next question.
Maybe I missed it because I missed the first few minutes of your presentation, but did you also cooperate with the Open BTS project, which also uses the USRP and also uses that as a base station for GSM in software?
Yes, I'm very well aware of Open BTS, and I'm in close contact with David Burgess, who develops Open BTS, and we have a lot of exchange of ideas and whatnot. I personally believe the architecture of a BTS does not contain too much that can be used for passive surveillance. The reason being that the BTS is the clock master. Yeah. It does not synchronize to any other signal, but it emits the synchronization sequence to which everyone else, both the actual receiver and any eavesdropper, have to lock onto the signal. So if you develop a passive sniffer then it has to synchronize to the BTS. It has to lock on a different signal, which is more is similar to a handset side, mobile station side implementation, not so similar to a BTS side implementation. But yes, generally there is a lot of exchange, and we're in good contacts, and that's very helpful. Yeah. Okay, I suppose the last question, because before we go to the next talk.
All right. Just a question if there's been already any hardware developments making custom hardware to help debugging or decoding the protocols.
Okay, so if I understood correctly, the question is whether there's any specific custom hardware for doing the decoding and so on.
Yeah, that has been developed by quote, us, unquote.
Yeah, as to my knowledge, publicly in the open source, open hardware community, there has not been any such custom development.
Is there, sorry, I'm interrupting, is there a regulatory issue with that?
No, there's no regulatory issue with that. I mean, regulatory issues arise mostly when transmitting is involved, and if you want to build custom hardware for receiving signals, there's no regulatory issue involved with developing the hardware. You might not be able, or might not be legal to use the hardware on commercial networks, but as long as you use like it for debugging OpenBSC or something like that, then it's a perfectly valid reason. Yep. Now, as far as custom hardware goes, the problem is that you would have to, all the integrated solutions, once again, you do not get access to them, right? You do not get access to the components, you do not get access to the documentation unless you're a handset maker who pushes tens of millions of units. Yep. Now, you could obviously build it in hardware using more traditional approaches, using hardware demodulation and a small DSP who decodes the signal in the baseband, like a traditional GSM receiver architecture. But then I don't really see the advantage of that. Yes, you can make the per unit cost cheaper. So rather than having to spend 1,000 whatever euros on the USRP, the custom hardware you can probably buy for like 100, 200 euros hardware cost. So it's mainly a cost optimization thing, but as far as complexity of development is involved, it doesn't make the problem any easier. You have to debug the electronics, you have to do a couple of PCB versions, all the involved people have to get the latest prototypes, so it's a lot of, it's much easier to tackle the problem in the software space than in the hardware space.
Yep. You mentioned also the downsampling?
Sorry,
You mentioned downsampling done to be able to cover because there aren't any components to digitize the full frequency signal?
It's the acoustics here completely, I'm sorry.
So should I just
Yes, please, don't speak to the microphone.
All right. You mentioned downsampling the analog signal in order to more easily be able to digitize it.
No, it was not downsampling, it was down-converting. Right? Downsampling is just reducing the sample rate. Down-converting is, well, you take the 900 megahertz, you shift it down to 10 megahertz. You take a spectrum out of the 900 megahertz, like 500 kilohertz width or 200 or whatever you want, and you shift it down to 10 megahertz. So your analog-digital converter doesn't have to run at a sample clock that's, like whatever.
And that is currently done in hardware already?
That is done by the USRP hardware, yes. The receiver front and what is here, the RFX 900 board, it takes the 900 megahertz, it down-converts it into actually baseband. It's a zero IF IQ down-converter. And then you have the I and Q components which are fed into 2 channels of an analog-digital converter. And then of the resulting signal, you can do a digital additional down conversion or resampling or anything still inside the board, and then it leaves the actual system and goes to the PC. So this is for the low-level technical details.
All right. Thanks.
Well, thank you. Well.
Okay, so we continue in approximately 5 minutes with GSM decryption, so that everybody can get a drink and be back here in 5 minutes.